Hi, so this is my fourth tutorial, and today we will be solving some problems involving coefficient of determination and also model fitting with autocorrelated errors. So, here is the first problem. The problem says that your friend says he has fitted a plane to 33 observations on x 1, x 2 and y, and his overall regression is just significant at 0.05 level of significance. Okay, that means your friend has fitted a multiple linear regression model with two regressors x 1 and x 2 and one response variable, and his test is significant. That means the fitted model is significant at 5% level of significance. Now, you asked him for his R square value, that is the coefficient of determination, but he does not know. You work out for him on the basis of what he has told you. So, what are the information given to you is that he has fitted a multiple linear regression model with two regressors x 1 and x 2, and his fit is significant at 0.05 level, but he does not know the R square value, where R square is the coefficient of determination, and it sort of measured the proportion of variability that is explained by the model. Now, you have to work out this R square value from whatever he has told to you. So, well, so what you know is that your friend has fitted a model like this, y equal to beta naught plus beta 1 x 1 plus beta 2 x 2 plus epsilon, and this model has been fitted for n equal to 33 observations. Okay. So, from these observations, I mean from this information, what you can do is that you can construct ANOVA table for this one. So, here is the ANOVA table. Okay. Source, sum of square, degree of freedom, and MS and the F statistic. Okay. So, the total degree of freedom is 32, because there are only 33 observations, and then the regression degree of freedom is 2, because there are 3 parameters, and the residual degree of freedom is 30. And of course, your friend has SS regression, SS residual, and SS total, and hence the MS regression, MS residual, and F value. Okay. So, what you know is that this F is significant. So, this F follows F distribution with the degree of freedom 2 30, and his test is just significant. So, that means the observed F value is just greater than or equal to the F value 0.05 at the level of, with the degree of freedom 2 30, which is equal to 3.32. So, you can assume that the observed F value is close to 3.32, and from here you have to compute the R square value. Okay, what is R square? R square is SS regression by SS total, that is the proportion of variability in y about mean, that is explained by the model. Okay. But what you know is that you know f, which is equal to ms regression by ms residual. So, you know the f value, you know their degree of freedom, but of course, you do not know separately the ms regression value and ms residual value. From f you have to compute R square. Okay. So, this is the problem. Well, we will see whether this R square can be written in terms of f. So, R square, which is equal to SS regression by SST, that I can write as SS regression, and SS total is equal to SS regression plus SS residual, right. And this one, I want to express this one in terms of f. So, this I can write as SS regression by ms residual. So, I will divide both the numerator and denominator by ms residual. So, this is SS regression by ms residual plus SS residual by ms residual. Okay. So, this one is equal to, so SS regression can be written as V 1 ms regression by ms residual, right, where V 1 is the regression degree of freedom, right. So, regression degree of freedom is V 1, and similarly here also I can write that this one as V 1 ms regression by ms residual plus V 2 ms residual by ms residual, where residual has degree of freedom V 2. Okay. So, this one is equal to, now I can write. So, M S regression by M S residual is nothing but f. So, this can be written as V 1 f by V 1 f plus V 2. Okay. So, now we can compute R square. So, this is how we can express R square in terms of f. So, we know that f is close to 3.32, and we know that our V 1 is the regression degree of freedom, that is equal to 2 in our case, and V 2 which is the residual degree of freedom, that is equal to 30. So, R square can be now written as 2 into 3.32 by 2 into 3.32 plus 30. So, which is equal to 0.1812. That means, you know what is R square. R square is the proportion of variability in y about mean, that is explained by the model. So, you can see here only 80% of total variability has been explained by the model. So, R square is, this means only 80% of total variability has been explained by the model. So, you can see that from this example, R square is a very good parameter to measure how good the fit is. See, the test is significant. So, the model is significant according to the global F test, but only 18% of the total variability has been explained by the model. So, which is quite low. Okay. So, we will consider another problem of similar type. So, this problem says that you are given a regression printout that shows a planar fit to x 1, x 2, x 3, x 4 and x 5 plus intercept of course, obtained from a set of 50 observations. The overall f for regression is 10 times as big as the 5% upper tail f percentage point. So, you have to compute how big is R square. Well, so here you are considering a model involving 5 regressors. So, y equal to beta naught plus beta 1 x 1 plus beta 2 x 2 plus beta 5 x 5 plus epsilon. Okay. And this model is fitted on 50 observations. So, we can quickly have a ANOVA table, so total degree of freedom, just the degree of freedom is important. Total degree of freedom is of course 49, and regression degree of freedom is, there are 1, 2, 3, total 6 parameters. So, the regression degree of freedom is 5 and the residual degree of freedom is then 40. 4. Well, so what we know is that we know that my V 1 is equal to 5 here, V 2 is equal to 44, and it says that the observed f value is 10 times the tabulated f value. So, for this test here f has degree of freedom f 544, and you have to find the tabulated value for this one at 0.05, and you can check that this value is equal to 2.43. Okay. So, what we are given is that your observed f value is 10 times bigger than this one. So, your observed f value is then is equal to 10 times of this tabulated f value, that is 2.43. So, which is equal to 24.3. Okay. And you know V 1, V 2, you know f. So, you can compute r square now. So, problem is that how big is r square. So, you know the formula that r square is equal to V 1 f by V 1 f plus V 2. So, here your V 1 is 5 and f is 24.3. So, 5 into 24.3 plus V 2 is, that is the residual degree of freedom, that is 44. So, here 73.43, that means 73% of the total variability in the response variable has been explained by the fitted model, okay, which is quite good. Okay, so, next we will be considering one problem from regression models with auto correlated errors. Okay, so, here is the problem. Consider the simple linear regression model y t equal to beta naught plus beta 1 x t plus epsilon t, where the errors are generated by second order autoregressive process. Okay, so, I hope that you can recall. So, here you can see this observations are collected sequentially in time. So, these are time series data basically, that is why it is denoted by t here. And in case of time series data, we know that this epsilon t, the error term, they are not independent, they are basically correlated, and here it is given that the errors are second order, errors are having second order autoregressive relation. So, epsilon t is equal to rho 1 epsilon t minus 1 plus rho 2 epsilon t minus 2 plus z t. So, this z t is independent with mean 0 and variance sigma z square. Here rho 1 and rho 2 are called auto correlation parameters. So, the problem is that you have to discuss how Cochran-Orcutt iterative process could be used in this situation. If you can recall, we talked about how to fit the regression parameters beta naught and beta 1 in case of first order autoregressive error. So, here instead of first order autoregressive error, we have second order autoregressive error. So, this is quite a straightforward problem. So, it says that what transformation would be used on the variables y t and x t, and how would you estimate the parameters rho 1 and rho 2. Well, so this is the problem. How do you estimate this parameter beta naught and beta 1 hat, beta 1 and beta naught in the presence of second order autoregressive error. Okay. So, let me start the solution for this problem. So, you need to feed this model y t is equal to beta naught plus beta 1 x t plus epsilon t, where this epsilon t is equal to rho 1, this is second order autoregressive, epsilon t minus 1 plus rho 2 epsilon t minus 2 plus z t, and this z t follows normal distribution with mean 0 and variance sigma z square. So, usually when we fit a simple linear regression model, we assume that epsilon t follows normal distribution with 0 mean and constant variance, and if it and they are also independent. So, if this is true, then we can estimate beta naught and beta 1 using the ordinary least square technique. But here it is given that this error term, they are not independent, they are correlated and they follow the second order autoregressive process. Okay. So, in this situation, how to fit this model? So, what we do is that we transform this response variable y t to y t dashed, which is equal to y t minus rho 1 y t minus 1 minus rho 2 y t minus 2. Okay. So, this is equal to, so this is equal to y t prime is equal to beta naught plus beta 1 x t plus epsilon t minus rho 1 beta naught plus beta 1 x t minus 1 plus epsilon t minus 1 minus rho 2 beta naught plus beta 1 x t minus 2 plus epsilon t minus 2. So, you understood. So, this is my y t, this is rho 1 y t minus 1 and then rho 2 y t minus 2, right. So, this can be written as beta naught minus rho 1 beta naught minus rho 2 beta naught plus beta 1 x t minus rho 1 x t minus 1 minus rho 2 x t minus 2 plus epsilon t minus rho 1 epsilon t minus 1 minus rho 2 epsilon t minus 2, right, epsilon t minus 2. Okay. And this one is equal to z t. So, this term is equal to z t. So, I can rewrite this one as say beta naught dashed plus beta 1, call this as x t prime. So, what you do is you transform y t to y t prime and similarly x t to x t prime. So, this is my x t prime plus z t. So, now in this transform model, so we have transformed y t to y t prime, where y t prime is given here. Similarly, we have transformed x t to x t prime, and as a consequence the error term has been transformed to z t. This z t is now independent. Now, z t are independent. Okay. So, and also we know that z t follows normal 0 sigma z square. So, the advantage of this one is that now we have a model like y t prime equal to beta naught dashed plus beta 1 x t prime plus z t, and here the error terms follow normal distribution with mean 0 and variance sigma square, and they are also independent. So, now you are in a position to apply your ordinary least square technique to estimate the regression coefficients beta naught prime and beta 1. But the problem is that this y t, you see here this y t prime that involves rho 1 and rho 2. Similarly, x t prime involves rho 1 and rho 2. So, we can't use this transformation unless we know the value of rho 1 and rho 2. So, y t prime and x t prime cannot be used directly as y t prime, which is equal to y t minus rho 1 y t minus 1 minus rho 2 y t minus 2 and x t prime, which is equal to x t minus rho 1 x t minus 1 minus rho 2 x t minus 2 are function of unknown parameters. Rho 1 and rho 2. So, unless you know, see, you are given the data x t and y t, you do not know rho 1 rho 2. Unless you know the value of rho 1 rho 2, how do you use this transformation, right? So, we need to estimate them, and we know that these are that autocorrelation parameter. What is this rho 1 and rho 2 are autocorrelation parameter for this second order autoregressive process. Rho 1 epsilon t minus 1 plus rho 2 epsilon t minus 2 plus z t. So, we need to estimate this rho 1 and rho 2. So, how to do that? You know that the E t, the observed value of E t epsilon t are Tth residual E t. Okay. So, what we do is that we fit this model y t equal to beta naught plus beta 1 x t plus epsilon t using ordinary least square technique and obtain the residual E I. So, we will fit this model, we do not ignoring the fact that they are autocorrelated. So, you fit this model, and once you have the fitted model, you can compute the residuals, and then you regress E I on E I minus 1 and E I minus 2. That is, you fit a model like E I is equal to rho 1 E I minus 1 plus rho 2 E I minus 2 plus some error Z t. So, you know epsilon i's, so you can fit this model, right. So, this is nothing but multiple linear regression model with 2 regressors. So, how do you estimate the parameter rho 1 and rho 2? You compute the least square function S rho 1 rho 2, which is equal to E I minus rho 1 E I minus 1 minus rho 2 E I minus 2, and you minimize this. So, you estimate rho 1 and rho 2 in such a way that this least square function is minimized, and what you do is that you just differentiate this S with respect to rho 1, that equal to 0 will give you one normal equation, and similarly partial derivative of S with respect to rho 2 is equal to 0. This will give you another normal equations. Let me write down those things. So, E I minus rho 1 E I minus 1 rho 2 E I minus 2 into E I minus 1, this is equal to 0. This is the first normal equation, and the second normal equation is E I minus rho 1 E I minus 1 minus rho 2 E I minus 2 into E I minus 2 equal to 0. So, you have two normal equations and two unknown. So, you can estimate, you can find rho 1 and rho 2, call them rho 1 hat and rho 2 hat. These are the least square estimate of rho 1 and rho 2. Okay. So, once you have this estimated values, now you can use this rho 1 hat and rho 2 hat to get the transform values. Y t prime is equal to y t minus rho 1 hat y t minus 1 minus rho 2 hat y t minus 2, and similarly you get x t prime, which is equal to x t minus rho 1 hat x t minus 1 minus rho 2 hat x t minus 2. So, now you can obtain y t prime and x t prime. So, these are the transform data, and now you are in position to apply ordinary least square to the transformed data. Y t prime equal to beta naught prime plus beta 1 x t prime plus z t. And here for the transform data, you know this z t, the error term on transform data, this follows normal 0 sigma z square. So, normal with mean 0 and constant variance sigma z square, and they are independent. So, you are in position to apply ordinary least square technique, and you apply ordinary least square technique here to get the estimated value, and the final fitted model is y t prime hat is equal to beta naught prime hat plus beta 1 hat x t. Okay. So, this is how you can fit the model in the presence of second order autoregressive error. Okay. So, this is called Cochrane-Orcutt procedure, and in a module called regression models with auto-correlated errors, we talked about the same technique for autoregressive errors with I mean first order autoregressive order. Okay. We solved the same problem when there exists a first order autoregressive error, and just now we solved for second order autoregressive error. Okay. So, let me consider one more problem. This is also to check whether there exists lag 1 autocorrelation or serial correlation. It says that the following 24 residuals. So, these are the residuals from a straight line fit are equally spaced in time and are given in time sequential order. That means, these residuals are obtained from a time series data, and they are equally spaced. I mean, the times are equally spaced. So, the question is there any evidence of lag 1 serial correlation? For these 24 residuals. So, it says that you use a two-sided test at level alpha equal to 0.05. Okay. So, you are given E I for I equal to 1 to 24. Okay. And how do you test that there exists lag 1 serial correlation or not? We know that for testing lag 1 serial correlation, we need to go for Darwin-Watson test. So, what we will do is that, so what is lag 1 correlation is that the correlation between epsilon u and epsilon u plus 1, this correlation is equal to rho, which is not equal to 0 if there exists lag 1 autocorrelation. So, what you have to test is that, so here you can see the errors are one step apart. So, we need to test that H naught rho equal to 0 against the H 1, that rho is not equal to 0. So, H naught says that there is no lag 1 autocorrelation in the residuals. H naught says that, and H 1 says there exists lag 1 autocorrelation. So, what we do is that we compute Darwin-Watson test statistic. What is that? That is D equal to sum over E u minus E u minus 1 square, u is from 2 to 24 here, by E u square for u equal to 1 to 24. And that you can check that you are given E i's, right. You are given E u for u equal to 1 to 24. So, we can compute this one. This is 2225 by 834, which is equal to 2.67. Well, so my D is 2.67, and we know that this D is the range of D is from 0 to 4, and it is symmetric about 2, we compute 4 minus d also. 4 minus d is equal to 1.33. And what you do is that for testing this two sided alternative, we compare this d value with dl and du, and this value you will get from the d table. So, for alpha equal to 0.025, because it is two sided test, that is why I am taking for alpha equal to 0.025, n equal to 24 and k equal to 1, because it is a straight line fit. So, there is only one regressor in the model, that is why k is equal to 1. You can check that your dl and du is equal to 1.16 and 1.33. Okay. Now, we need to think about the critical values for this one. Okay. So, what we have is that we have we know that my d is equal to 2.67, my 4 minus d is equal to 1.33, and my dl and du is equal to 1.16, 1.33. Okay. So, if d is less than dl or 4 minus d is less than dl, you reject H naught. That means, if the Darwin-Watson test statistic is small, then you reject H naught. Rejecting H naught means there is no autocorrelation. Okay. Let us see what is this d value. D is 2.67, which is not equal to dl, and similarly 4 minus d, which is equal to 1.33, which is not strictly which is again not less than dl value, which is 1.66. So, here d value is large. So, we reject H naught. Rejecting H naught means well, so d is not true. Okay. So, this is not true. So, we are not going to reject H naught, we accept H naught, because as my d, which is equal to 2.67, which is not equal to dl, which is not less than equal to 1.16. So, this is not true. So, I will accept H naught. So, accepting H naught means no, there is no lag 1 autocorrelation or serial correlation. Okay. So, this is the first one, and also you can do what you can do is that you check with this one, if of course, you will get the same result. If d is greater than du and 4 minus d is greater than du, then it says that you accept H naught, which is equal to rho is equal to 0. Is it so? This is the test in terms of du values, d upper values. So, d is greater than du, yes, d is 2.67, which is greater than du 1.33, and also my 4 minus d, which is equal to 1.33 is greater than or equal to du, that is 1.33. So, both are true. So, we accept H naught. Accepting H naught means there is no lag 1 autocorrelation or serial correlation in the data. Okay, so here we have used Darwin-Watson test to test whether there exist serial autocorrelation, lag 1 autocorrelation or not. So, intuitively when the d value that is the Darwin-Watson test statistic, when that is small, that means there exists autocorrelation, right. And here you can see that the d value is not smaller than the d lower value. That is why finally, the conclusion is that there is no lag 1 autocorrelation in the data. Okay. Well, so we talked about this problem, and still we have some time. So, we can sort of recall the parameter estimation technique in case of in the existence of first order autoregressive errors. So, this is what the Cochrane-Orkut method, and this says that how to estimate this parameter beta naught and beta 1 when there exist first order autocorrelation or among the errors. Well, and this epsilon t, they are not independent 0 sigma square, they are having the first order autoregressive error. And what we did there is that we transform y t to y t prime, which is equal to y t minus rho y t minus 1, and we can finally check you can finally check that this y t prime is equal to beta naught prime plus beta 1 x t prime plus z t, and here z t is equal to epsilon t minus rho epsilon t minus 1, and we know that this z t, this transform error, they are independent, and that is why you can use ordinary least square technique to this transformed data, but the problem again is that this x t prime and y t prime, they involve some unknown parameter rho, and we talked about how to estimate those rho. I mean the similar technique, I mean just repeating the things here. So, you feed the model using the ordinary least square technique, ignore the thing that assumption is not true here, and fitting the ordinary least square technique, you will get the residuals E i's, and then you regress E I on E I minus 1, right, and you feed this model, that is E I is equal to rho E I minus 1 plus z t, and the least square estimate of rho is this one. You can check that you have to estimate rho in such a way that this is minimum. So, the rho value is equal to this, and using this rho, now you can transform the data y t to y t prime, similarly x t to x t prime, and now you know that this transform data or the transform model has error z t, which is normal 0 sigma square, and they are independent. So, you can apply ordinary least square technique to this transform data, and you can happily estimate beta naught hat and beta 1 hat. Okay. So, this is sort of just we solved the same problem for second order autoregressive error today. Well, so that is all for today. Again in the next tutorial class, we will be solving some randomly selected problems. Thank you very much.